Good afternoon, dear friends. Welcome you back to today's session on online gate coaching classes. I hope you had a good rest yesterday night and you are fresh for today's online class. So before we start today's session, actually I'd like to present principal stresses and principal strains in today's session. So before we start today's session, I'd like to answer some of the queries, doubts raised by the students based on yesterday's session. SSSreddy630@gmail.com has got one question. Sir, JCB with wheel, is it dynamic UDL or not? So that's what he's asking. So JCB actually is not a UDL at all. JCB, the entire load which it is lifted by the crane is transferred to the road surface through its wheels. So generally wheel loads are taken as point load reinforcement. What about using other materials like copper and silver? If you consider RCC, reinforced cement concrete, we use steel. Okay, it's not iron. Okay, we are not using iron, we are using steel as reinforcement. We are using steel as the reinforcement. The basic reason for steel being used is when compared to copper or silver, steel is much cheaper. You cannot use copper and silver. And second thing is the tensile strength of the steel is very high. The tensile strength of the steel is very high. The bond between concrete and steel is good. The bond between concrete and the steel is good. In addition, the coefficient of thermal expansion for concrete and steel is more or less same. So this will give a lot of equilibrium equations. We know the number of equilibrium equations are 3 for a general case. That is, algebraic sum of all the moments is equal to 0. Algebraic sum of all the horizontal forces is equal to 0. Algebraic sum of all vertical forces is equal to 0. So that is about statical indeterminacy. In the case of kinematic indeterminacy, we call it as the degree of freedom. We call it degree of freedom. Say for example, if you take a fixed support, at fixed support, the support cannot move in the horizontal direction, the support can't move in the vertical direction, and the support cannot rotate also at that point. So at a fixed support, there is neither horizontal movement, there is neither vertical movement nor a rotation possible. So at fixed support, the degree of freedom is equal to 0. The degree of freedom is equal to 0. Similarly, if you take a hinged support, rotation is possible, whereas horizontal movement is not possible and vertical movement is not possible at the hinge. So the degree of freedom at hinged support is equal to 1. The degree of freedom at a hinged support is equal to 1. If you take a roller support, in case of a roller support, it can move in a direction parallel to the roller, that is horizontal roller. If you take horizontal direction, it can also rotate about the point. So only restricted movement is the vertical reaction, that is vertical direction perpendicular to the direction of motion of the roller. So in case of a roller support, we have 2 degrees of freedom. So what the degree of kinematic indeterminacy is nothing but the degree of freedom of the structure. So let us take a fixed beam. Which is supported at both the ends. So if you take at left support, the degree of freedom is equal to 0. If you take at the right support, the degree of freedom is again 0. So total degree of freedom for the structure, fixed beam, is equal to 0 plus 0. So the fixed beam is having a degree of freedom is equal to 0. So it is kinematically determinate structure. A fixed beam is a kinematically determinate structure, whereas it is statically indeterminate to third degree. See the difference, okay? The fixed beam is kinematically determinate structure. Now if you come to a cantilever is fixed at one end and it is free at the other end. So if you take the degree of freedom at the fixed end, the degree of freedom is equal to 0. At the free end, there is no support at all there. So there are 0 degrees of freedom. So it is again determinate, kinematically determinate structure. So if you take a simply supported beam, if you take a simply supported beam, it is supported by a hinge at left end and roller at the other end. Okay, it is supported at a hinge at the left end and roller at the right end, or vice versa, no problem. So if you take a hinged end, okay, we take a hinge support, the degree of freedom is 1. If you take at the roller support, the degree of freedom is 2. So total degree of freedom is 3. So a simply supported beam is kinematically indeterminate to third degree. So a structure for which the degree of freedom is equal to 0 is called kinematically determinate structure. If it is more than 0, then it is kinematically indeterminate structure. So that is the difference between static indeterminacy and kinematic indeterminacy. I hope Divyakant49@gmail.com has raised this question. I think this explanation has satisfied you, Mr. Divyakant. Swarupa2000@gmail.com. Sir, explain briefly about principle of superposition with example. Principle of superposition is when you draw the free body diagrams, when you superimpose one plane over the other plane, so the summation of forces or the resultant force must be equal to what is there in the original drawing. So that is what we call as the principle of superposition. I have explained this while solving some of the problems of the elongation by drawing free body diagrams, the principle of superposition. Divyakant49@gmail.com. Hi sir, please tell the answer. Distribution factor of a member depends on which joint? Hinge joint or rigid joint? See, it is distribution factor is in moment distribution. It comes in structural analysis. I think in the next phase we will answer this question, because if you have to answer the distribution factor, I have to explain you the entire moment distribution concept. So that is it will take a lot of time. So anyhow we are dealing with structural analysis. That time we will answer this question. Vanaja1073@gmail.com. In beam where we can see upward loading. Okay. Second question is where we can see uniformly varying load in beams and arches. So upward loading is possible whenever, say for example, you are resting a foundation. When you rest the foundation beam on the ground, so the ground reaction acts upwards on the beam. So such a cases we get upward loading. Uniformly varying load in beams and arches. Practically uniformly varying loads you generally don't see. Mostly you get uniformly distributed loads only in practice. In peculiar conditions we get uniformly varying loads. Particularly if you take a dam subjected to water pressure, the water pressure increases with the depth. So at the top the water pressure is 0, at the bottom water pressure is W into H, so it varies uniformly from 0 to WH. So such a cases, and similarly you take a retaining wall subjected to earth pressure. These are the cases where you get such varying loads. Deepak 1999 2222@gmail.com. Sir, I have a doubt. In case of a beam is constructed of span L with RCC, if span L by 2 portion, I didn't get the question in full. L by 2 portion of a beam. If a span L by 2 portion of a beam is collapsed due to some reasons, if we use a wooden beam of same dimensions is replaced in that L by 2 portion, then it called a flitched beam. No, it's not correct. What you are saying is not at all correct. You are saying that a beam of span L is of RCC and the L by 2 portion, that the half length of the beam has collapsed, and the other half, the collapsed portion you want to put with a wooden beam. So whenever we try to reinforce the beam, we reinforce with a material which is having higher strength or higher Young's modulus than the original material. So generally, whenever there is a failure in RCC, we do reinforcement with carbon sheets. Okay, we do carbon fiber reinforced composite material wrapping we do for reinforcement. So wooden beams, wood beams are not used there. So your idea is not correct and it's not practicable. So Samir Mohan MADO 74. Thank you, sir. You are explaining every point so well. Sir, this is the 5th day from starting. Only 2 subjects are being taught. So in each phase, we are planning to teach 2 subjects. Now in this phase, we are teaching geotechnical engineering and structural engineering. In part of structural engineering, we are dealing mechanics of solids or solid mechanics. So in the next phase, the other subjects will be taught. And I am really thank you for appreciating that our lectures are very nice and you are enjoying our lectures. Thank you, Mr. Samir, yeah, thank you, Mr. Samir. Sai Kumar Reddy, Yaluri. In bending moment diagrams, maximum bending moment is at center and maximum bending stress is at extreme fibers. Is bending moment and maximum bending stress are not equal? Bending moment is a moment. Bending moment is moment. Due to bending moment, we get bending stress. At a section, find out the bending moment. Due to this bending moment, at extreme fiber, we get the bending stress. Bending stress is there across the entire depth. Maximum bending stress will occur at the extreme fiber. That is equal to M by Z. Bending stress is equal to M by Z. Z is the section modulus. So bending moment is different from bending stress. So don't get confused of thickness dz. Find out what is AY bar of this small strip and integrate it between the limits theta to pi by 2. Integrate it between the limits theta to pi by 2. So that will do our job. So we are taking a small strip within this circular portion. Okay, we are taking a small strip and we are trying to find out the AY bar of the small strip. So from there we are integrating and getting the AY bar for the total area above section AA. Okay, so to do this, we have to first find out what is the width of this strip. Okay, the width of the strip. So width of this small element B is equal to, from the diagram you can see this is, I want to find out the width of this small element V. So you consider that the angle made by this element with the neutral axis is phi. Okay, this with the phi. So now automatically the width of the element is equal to 2 into d by 2 cos phi. Okay, because two sides, half of the is d by 2 cos phi. So d by 2 cos phi. So this is d by 2 radius. This is radius. So I want this length. This length is d by 2 cos phi. Okay, this is d by 2 cos phi. And same way this is also d by 2 cos phi. So the width of the total element is 2 into d by 2 cos phi or d cos phi. Okay, d cos phi. Similarly, what is z? What is z? Vertical component. Vertical component. So vertical component is d by 2 sin phi. Okay, d by 2 sin phi. We want dz actually. We want dz. So take the first derivative, d by 2 sin phi. If you take d by 2 constant, so it will remain same. If you differentiate sin phi, it will be cos phi d phi. It will be cos phi d phi. So dz is equal to d by 2 cos phi d phi. So now what is the area of this small element? It is width of the element multiplied by the thickness of the element dz. So b into dz. Area is equal to b into dz. So d cos phi into d by 2 cos phi d phi. Or if you simplify this, d square by 2 cos square phi d phi. This is area of the element. Now what is moment of this element? A y bar, moment of this small area of the element. So moment of this small area about the element is area into z. Because if you see, the distance is, this distance is z. So the distance of the centroid of this element about the neutral axis is z. So the moment of the small area is equal to area of the small element into z. So d square by 2 cos square phi d phi into z is equal to d by 2 sin phi. We already taken this. So this becomes d cubed 4 by 4 cos square phi sin phi d phi. So this is the area of the small strip. But this is the AY bar of the small strip. But we want moment of area completely above the section AA, about the neutral axis. So we have to get integration. We have to integrate this small AY bar, delta AY bar, to get the total area AY bar. So integral of theta to pi by 2 d square by 4 cos square phi sin phi d phi. So if you integrate this and substitute the limits theta and pi by 2, you get the AY bar. Okay, you get the AY bar. Once you get the AY bar, Q is equal to F by BI into AY bar. So if you substitute that, you will get the shear stress distribution. I hope this has clarified you. This has clarified your doubt. So for triangular section, it is in fact very easy. For triangular section, there is no problem. See, this is the section where you want to find out the shear stress, let us say. So you have to consider all the area above the section. All the area above the section. Area of the section is half of base into height. Okay, centroid will be at h by 3 from the base. So AY bar you can easily compute in case of a triangle. Only for circle you need certain integration part. So this can be done very easily. So I hope you understood that particular problem. Sai Kumar Reddy Yaluri. Thank you, Sai Kumar Reddy. You are saying that the lecture is very useful rather than videos in the YouTube, and I would like to you are thanking myself and my supporting team. Thank you very much. Your doubt is, in a beam where maximum shear stress and bending moment will occur, and give practical exams. In beam, where does maximum shear stress occur? That's what I am trying to explain in this class. The maximum shear stress distribution, if you take a rectangular section, the maximum shear stress occurs on the neutral axis. Okay, the maximum shear stress occurs on the neutral axis. If you say take a circular section also, the maximum shear stress occurs on the neutral axis. So depending upon the section, you have to find out where the maximum shear stress occurs. Maximum bending stress occurs on the neutral axis always. There is no confusion. Okay. Maximum bending stress occurs always at the extreme fibers. Maximum bending stress always occurs at the extreme fibers, whereas maximum shear stress occurs sometimes at the neutral axis and sometimes it may be different. You have to find out depending upon the section given. Okay. I have explained different types of sections where you have to find out the maximum shear stress across the depth. Praveenkumar@gmail.com. Thank you for the great lecture, sir. Thank you, Mr. Praveen. Sir, we will locate the centroid of any shape, circle, etc. Is it possible to locate the moment of inertia? Okay, moment of inertia is not a point. Moment of inertia is not a point. It is a value. It is a second moment of various UDL and couple act at support. How varies the bending moment in the beam? This question is not clear. UDL cannot act at the support. UDL cannot act at the support. A couple can act at the support. So whatever it is, see, you should have a clear concept. The question is asked by Sricharan Kolopalli. Please have a concept for whatever loading it is. Drawing of the bending moment and shear force is only by concept. So first of all, if you take a shear force diagram, if you take a simply supported beam, so to draw the shear force diagram and bending moment diagram for a shear force beam, first step is you have to find out the reactions. Okay, you take moments about any of one support, either left support or the right support, and equate moments of all the forces equal to 0 about the support. So, and you also use your vertical equilibrium equation. Okay, so vertical downward loading must be equal to upward loading. Generally, the two vertical reactions will be acting upward. So VA plus BB must be equal to total downward loading. So just general. So that way you find out the reactions first. Once you find out the reactions, you draw the shear force and bending moment diagram by considering a section at a point. Consider a section at a point and find out shear force there by algebraic sum of all the forces either to the right or the left. Bending moment, if you want, you take algebraic sum of moments of all forces acting either to the right or to the left. So the concept, if you have, you can draw the shear force and bending moment diagram for any type of loading, either it is a couple or it is a UDL or it's a varying load. So number of examples I have given in my presentation. So I request you to go through the PPT of shear force and bending moment diagrams. A couple problems I have given, quite a few number of problems I have solved with couples. So you please go through that. So friends, today we are going to discuss the new topic. We are going to discuss the new topic is principal stresses and principal strain. So before going to the new topic, let us complete the questions. For a given shear force across a symmetrical I section, the intensity of shear stress is maximum at for a symmetrical I section. So where will be the maximum shear stress will be occurring? Shear stress will be occurring at the neutral axis, which is nothing, it is passes to the centroid. So the maximum shear stress occurs at the neutral axis for a symmetrical I section. So the answer is extreme fibers, centroid of the section. So B is the correct answer. B is the correct answer. At any of the four joints, AY bar is equal to, take any four joints, AY bar is equal to 75 is the width. Okay, 75 into 50 is the area. Okay, 75 into 50 is the area, and 125 is the distance. So AY bar is equal to 75 into 50 into 125. So this is the AY bar. So from which we get Q. Q is equal to F into AY bar by I. So if you substitute that, you get Q What is that? That is the shear flow at any glue joint, at any glue. So that is 4, that is B is the correct answer. So simply we have to use the same formula. Tau is equal to F into AY bar by IB. If a beam of rectangular cross section is subjected to a vertical load shear force V, the shear force carried by upper one third of the cross section is. So we have a rectangular cross section. We have a rectangular cross section, and he wants us to find out what is the shear force carried by upper one third. So this is D by 3. The total depth is D by 3. So upper D third portion, how much shear force it is carrying. So to find out that, we have to find out first shear stress distribution. Okay, we have to find out the shear stress distribution. So let us consider a small strip in this portion at a distance of y, having a thickness of dy. Okay, so what is the area of this small strip? This area of this small strip is B into dy. What is its moment? B into dy into y. Okay, B into dy into y. So that is the moment. So if you integrate it, you get the total AY bar. If you integrate it, you get the total Y bar. So see here, F tau is equal to F into AY bar by I. So F shear force is V, F is V, okay. D by 2 minus Y, D by 2 minus Y into B into D by 2 plus Y by 2. So this is straight away we are calculating the shear stress distribution for this area. Okay, instead of that, better we integrate it also. So if you integrate, what are the limits? D by 6 to D by 2. So this is y is equal to D by 2 to y is equal to D by 6. So if you just integrate this, you are going to get the answer. Integration is always best for this problem. The shear stress of the neutral axis in a beam of triangular section with a base of 40 mm and a height of 20 mm subjected to a shear force of 3 kilonewtons is. So the base of the triangular section is 40 mm. The height is 20 mm. It is subjected to a shear force of 3 kilonewtons. He wants us to find out the shear stress at the neutral axis. The shear stress at the neutral axis. Okay. So neutral axis will be at a distance of h by 3 from the bottom or 2h by 3 from the top. So this is the neutral axis. So at a distance of 2 by 3 into 20, so 13.33. At a distance of 13.33, the neutral axis is available. Okay. So what is the width here? You take the similar triangles, big triangle and the small triangle. Okay. Take the width. What is the width now? 40 by 20 is equal to B by 13.33. 40 by 20 is equal to B by 13.33, from which we get B is equal to 26.67. So maximum shear stress is equal to F into AY bar by IB. Shear stress distribution. So AY bar is what we have to consider. We have to consider all these AY bar. Top portion we have to consider. All top portion we have to consider. So that is area of the small triangle. So half of base into height. Okay. Half of base B into height. And its distance is 1/3 of 13.3. So AY bar we get. So moment of inertia of the section is BH cubed by 36. So we get, directly substitute, we get the Q neutral axis. But on the other hand, we can simply solve this problem if we remember the equation I did yesterday. So the shear stress of the neutral axis for a triangular section is 4/3 of average shear stress. 4/3 of average shear stress. So 4 by 3 F by A. So 4 by 3 F is given. Okay, F is given. Area is half of base into height. So 10 Newton force. Whether you do from the fundamental or if you just remember this 4/3 of average shear stress, you can get in one step. In case of a triangular section, the shear stress, the maximum shear stress, the shear stress of the neutral axis is 4/3 of the average shear stress. A symmetric eye section with a width of each flange is equal to 50 mm, thickness of each flange is equal to 10 mm, depth of web is equal to 100 mm, and thickness of web is 10 mm, is made up of steel. It is subjected to a shear force of 100 kilonewtons. Find the magnitude of shear stress in the web at its junction with the top flange. So he wants us to find out the shear stress here, okay, in the junction of flange and web in the web. We want in the web. So width of the flange is 50 mm. So this is the top flange, this is the bottom flange, width is 50 mm, thickness is 10 mm, depth of the web is 100 mm. This is the web, vertical web, 100 mm depth. Okay. So this is the thickness of the web is 10 mm. This thickness is 10 mm. So for symmetrical section, the neutral axis is the centroid here. So from the top, this passes through the centroid, the neutral axis. So it is at the center. The shear force is 100 kilonewtons. Okay. So shear stress at any distance from the neutral axis is equal to F into Ay bar by IB. So let us consider moment of the area above the point considered about the neutral axis. So what is Ay bar? Ay bar is Ay bar is just wait. Oh yeah. Ay bar is the entire flange portion. We have to consider, because we are calculating at the junction of the flange and web, the entire above portion we have to consider as the Ay bar. Okay, Ay bar. But we are calculating in the web. We have to calculate in the web. So that point you have to keep in mind. So Ay bar is equal to 50 into 10. Okay, 50 into 10. 50 into 10. That is this area. 50 into 10 is this area. Moment about the neutral axis. This depth is 50 plus half of this 10 is 5. So 55. 55. 50, 10 into 55. So this is Ay bar. So moment of inertia is, for the symmetrical section, the vertical web portion, thickness is 10, depth is 100, 10 into 100 cube by 12. For two flanges, 50 into 10 cube by 12 about their own axis. About centroidal axis, we have to add Ay square. So 50 into 10 is the area. Y is 55, so 55 square. Such two flanges are there, so 2. We get the total moment of inertia. Total moment of inertia. Now, width of the section under consideration. This is very important. See, width of the section under consideration. So you are calculating in the web. So the width you have to consider is the width of the web or thickness of the web, which is equal to 10 mm. You should not consider the width of the flange, because he has asked you to find out the magnitude of the shear stress in the web at the junction. So at the junction in the web, so you have to use the thickness of the web, width of the web, nothing but the thickness of the web. So here tau is equal to F into Ay bar by IB. B should be equal to 10 mm width of the web. So if you substitute, you get what is the shear stress there. The cross section of a built up wooden beam, as shown in the figure, is subjected to a vertical shear force of 8 kilonewtons. The beam is symmetrical about the neutral axis, and the neutral axis also is given. The moment of inertia about neutral axis is 1.5 into 10 to the power of 9 mm to the power of 4. Considering that the nails at the location P are spaced longitudinally along the length of the beam at 60 mm, each of the nails at P will be subjected to the shear force of. So we have to find out the shear force at each nail. So we have to find out what is the shear flow first. Okay, find out the shear flow. We will get the answer for this. So let us consider the shear flow at any section 1-1. So let us any section you take 1-1. This anything is okay. So if you take this section 1-1, the shear flow is equal to tau into B. The shear flow is equal to tau into B. So it is nothing but F into Ay bar by I. F is given as 8 kilonewtons. Moment of inertia about the neutral axis is he has given. I is he has given. So spacing of nails along the length is 60 mm. 60 mm. So moment of the area beyond the section under consideration about the neutral axis, if you want Ay bar, that is nothing but 50 into 100. Okay, this is 50, this is 100. So 50 into 100 into about the center point is 150. Okay, it is 150. See, about the center point, this is the center point, this is 150. So y bar is equal to 150. So the width is 50, depth is 100. So 50 into 100 is the area. 150 is the distance of the centroid from the neutral axis. So Ay bar is equal to 150. So if you substitute, you will get Q. Q is equal to F into Ay bar by I. You will get what is the shear stress. And if the spacing is 60, so the total shear force resisted by each nail is equal to shear flow into spacing. So 4 into 60, 240 newtons. Just use the concept, that's all. So we'll see some of the problems in mechanical engineering GATE question papers, previous question papers. The ratio of average shear stress to maximum shear stress in a beam with square cross section is. So this already I have explained you in my previous class. For a rectangular cross section or the square cross section, the shear stress varies as a parabolic distribution. The maximum shear stress occurs on the neutral axis, which is equal to 3 by 2 times the average shear stress. So he is asking us the ratio of average shear stress to maximum shear stress. So it will be reverse of 3 by 2, it is 2 by 3. Okay, it is 2 by 3. Tau average by tau max is equal to 2 by 3. Tau max is equal to 3 by 2 times tau average. So tau average by tau max is equal to 2 by 3. The transverse shear stress acting in a beam of rectangular cross section subjected to transverse shear load is. Transverse shear stress acting in a beam of rectangular cross section subjected to a transverse shear load is variable with maximum at the bottom of the beam. Variable with maximum at the bottom of the beam. Wrong. It is wrong. At bottom of the beam, the shear stress is 0. Variable with maximum at the top of the beam, it is also wrong, because at the top of the beam also the shear stress is 0. Uniform. No, it is not correct. The shear stress distribution is not uniform. Variable with maximum at the neutral axis. Correct. Maximum at the neutral axis. And we know tau max is equal to 3 by 2 times tau average. So this is what some of the problems. You can solve these problems by simply using the concept. So there's nothing more than that you have to do. You simply use concepts. So by using the concept tau is equal to F by IB into Ay bar, you will be able to solve any problem. It is not at all difficult. Okay, it is not at all difficult. So that is about the shear stress distribution. I hope I will try to provide some more problems in my notes, which I am going to give at the end of the sessions, or after completing all the session. I am going to give notes. There I will give some more problems which have been formulated by us. The same problems I am going to give to you in the notes also. You can solve those problems also. Along with the problem, I also have given detailed explanation for the solution also I have given. So you can easily solve those problems. Now let us go to today's topic, which is principal stresses and principal strains. Actually, principal stresses and principal strains is not in the GATE syllabus 2020. If you look at the GATE syllabus 2020, this topic is not there directly. But theories of failure topic is added. So if you want to understand the theories of failure, you need some knowledge of principal stresses and strains. You need certain knowledge of principal stresses and strains. So I will try to provide the basic knowledge about the principal stresses and strains and how to draw a more circle of diagrams and solve few problems so that you are ready for theories of failure topic. You are ready for the theories of failure topic. So let us proceed to principal stresses and strains. First, before understanding principal stresses, we should understand principal planes. If you consider any three-dimensional body, if you consider any three-dimensional body, there will be different loads acting in 3 dimensions. Okay, there will be different loads acting on 3 dimensions. Okay, if you consider a three-dimensional scenario, the stress tensor is having sigma x, sigma y, sigma z. Okay, sigma x, sigma y, sigma z, they are all direct stresses. Tau xy, tau yz and tau zx are all shear stresses. So overall, the stress tensor will have 6 independent stress components. In a 3-dimensional situation, we have 6 independent stress constants. They are sigma x, sigma y and sigma z are normal stresses. Tau xy, tau yz and tau zx are the shear stresses. So if you consider these, if you take any plane, if you consider any plane within the material or within the body subjected to external forces, the plane within the material will have 2 types of stresses on any inclined plane. On any inclined plane, there are two types of stresses. One stress is normal to the plane and one stress is called tangential to the plane. If you consider in a 3-dimensional body, any plane inclined within the body, the inclined plane will be subjected to 2 stresses. One stress is normal to the plane and the other stress is tangential to the plane. This tangential stress is also called as the shear stress. Okay, it is also called as the shear stress. So if you consider any inclined plane in a material, there is one normal stress acting perpendicular to this inclined plane and one stress acting tangential to this inclined plane. So this is also called shear stress. So there is one normal stress which is perpendicular to the plane and there is one shear stress which is acting along the plane. So any inclined plane will have a normal stress and also a tangential stress. Now let us understand what is a principal plane. A principal plane is defined as such a plane where the stress is wholly normal and the tangential stress is equal to 0. So you are considering an inclined plane. Generally, on any inclined plane, we have a normal stress and we also have a tangential stress. But principal plane is defined as a plane where there is only normal stress acting on the plane and the tangential stress is 0. So a plane where there is no tangential stress, where there is no shear stress, where the stress is only normal, such a plane is called as a principal plane. A principal plane. So I hope you understand. If you consider any plane, inclined plane, generally we have a normal stress and we also have a tangential stress. So if the tangential stress is 0, such a plane is called as a principal plane. So that means in case of a principal plane, the only stress is normal stress. So there is only stress in a direction perpendicular to the inclined plane. So there is only one stress perpendicular to the plane. So that is called as a principal plane. And the normal stress acting on the principal plane is called as a principal stress. The normal stress acting on a principal plane is called as a principal stress. So if you consider a 3-dimensional situation, we have 3 principal planes. Please note that these principal planes will be mutually orthogonal. mutually orthogonal. That will be mutually perpendicular to each other. So if you consider a XY plane, a YZ plane, a ZX plane. So three mutually perpendicular planes we have. So three mutually perpendicular principal planes will be there. In a three-dimensional situation, we have three principal planes. So if we have three principal planes, we have three principal stresses. Okay, we have three principal planes, so we'll have three principal stresses. The highest of all the three principal stresses is called as major principal stress. So major principal stress is the highest of all the three principal stresses. Okay, the least of the three principal stresses is called as minor principal stress. Okay, the major principal stress, the minor principal stress, and the one intermediate to these two is called as intermediate principal stress. Okay, major principal stress, minor principal stress, and the intermediate principal stress. So try to understand the concept. A principal plane is a plane on which the stress is wholly normal and there is no tangential stress or shear stress. So a plane where there is no shear stress, only normal stress is existing, that plane is called as a principal plane. And for a three-dimensional problem, we have three principal planes. One is a major principal plane carrying major principal stress perpendicular to that, minor principal plane perpendicular to the major principal plane, okay, perpendicular to the major principal plane, carrying the least principal stress or the minor principal stress. In addition, we have intermediate principal plane perpendicular to these two, the carrying the intermediate principal stress. Now, if you consider a two-dimensional situation, most of the occasions we reduce the problem to a two-dimensional situation. Okay, so if you consider a two-dimensional situation, we have only two principal planes. We have two principal planes. One is a major principal plane, and automatically the second one is a minor principal plane. So similarly, we have two principal stresses. One is the major principal stress, and the other one is the minor principal stress. So we have a major principal plane and a minor principal plane, a major principal stress and the minor principal stress in case of a two-dimensional problem. So this you have to understand the concept. So let us try to find out the principal planes and principal stresses for different conditions. Now let us consider a very simple case, a uniaxial force. Okay, let us consider this block. So let us consider this block and a horizontal force of P is applied. A horizontal force of P is applied along the axis. So this is called as a uniaxial stress system. This is a uniaxial stress system because only one stress is applied, one force is applied along the axis. So it is called as a uniaxial stress system. So now consider any plane BC. Okay, consider any plane BC at an angle of theta to the vertical plane. So this is the vertical plane. Okay, this is a vertical plane. If you consider any plane BC at an angle theta, what is the stress distribution now? If A is the area of cross section of this vertical plane, then P by A is the stress in this direction. Stress in the horizontal direction we call sigma x. So this is sigma x direction. Stress in the x direction. Okay. So if you consider a plane BC, at an angle of theta to the vertical plane, we'll have a normal stress perpendicular to BC and we have a tangential stress along the plane BC. So any plane, inclined plane, will have a normal stress perpendicular to the plane and a tangential stress which is along the plane. So we are applying stress in sigma x in the x direction. So due to this, we are getting sigma normal and sigma tangential on any inclined plane. So without going much into details, we can find out that the normal stress sigma n on this inclined plane is equal to sigma cos squared theta, and the tangential stress is sigma sin 2 theta by 2. So we have a normal stress, we have a tangential stress. So the resultant stress is, see, this is a normal stress, this is tangential stress, and there will be a resultant stress. There will be a resultant stress. So the resultant stress will be equal to under root of sigma n square plus sigma t square. That will be the resultant stress, sigma r. So where does this resultant stress will act? Tan phi is equal to sigma t by sigma n. So it is acting, see, this is the sigma t, this is sigma t, this is sigma n. The resultant stress will act somewhere here. If you take this angle is phi, tan phi is equal to sigma t by sigma n. So from this equation you can see, where does sigma n is maximum? Sigma n is equal to sigma cos square theta. So when it will become maximum? When cos square theta is equal to 1. Sigma n is equal to maximum when cos square theta is equal to 1. So theta is equal to 0 degrees. Cos square theta is equal to 1 means cos square theta is equal to 1 means cos theta is equal to 1. Cos theta is equal to 1, theta is equal to 0 degrees. So maximum normal stress sigma n max is equal to theta is equal to 0 degrees. So sigma n is equal to sigma x. Sigma n is nothing but sigma x. Similarly, what is the maximum shear stress? Maximum shear stress is sin 2 theta by 2. When sin 2 theta becomes 1, we get maximum shear stress. So sin 2 theta y is equal to 1, 2 theta is equal to 90 degrees. So theta is equal to 45 degrees. Okay, theta is equal to 45 degrees or 135 degrees. Okay. So maximum tangential stress, if you substitute here, sigma t is equal to sigma into sin 2 theta by 2. Sin 2 theta by 2 becomes, sin 2 theta becomes 1. So sigma t is equal to sigma by 2. So please note, when you are applying a stress sigma x horizontal direction, the maximum shear stress that is developing will be equal to sigma x by 2. The maximum shear stress that is developed is sigma x by 2 at an angle of 45 degrees. At an angle of 45 degrees to the plane on which the normal stress is acting. Plane on which the normal stress is acting. Now let us take another case where now we are applying force into mutually perpendicular directions. So in this direction P1, in this direction P2. Okay, we are applying P1 in this x direction, P2 in the other direction. So we have stress sigma x in the x direction, sigma y in the y direction. So because of this, again if you consider any inclined plane, we have normal stress sigma n, tangential stress sigma theta. Okay, okay, normal stress sigma n, tangential stress sigma t. So you can find out the normal stress is equal to sigma x cos square theta plus sigma y sin square theta, or it is also written as sigma 1 plus sigma 2 by 2 plus sigma 1 minus sigma 2 by 2 cos 2 theta. So this equation we can write it as sigma 1 plus sigma 2 by 2 plus sigma 1 minus sigma 2 by 2 cos 2 theta, because cos square theta you can write as 1 minus sin square theta, and simplify this, you get this. Okay, you get this equation. So sigma normal is sigma 1 plus sigma 2 by 2 plus sigma 1 minus sigma 2 by 2 cos 2 theta. The tangential stress is again sigma 1 minus sigma 2 by 2 sin 2 theta. Sigma 1 minus or sigma x minus sigma y by 2 sin 2 theta. So in this case, if you apply sigma y is equal to 0, if you apply sigma y is equal to 0, you get previous problem. You get previous problem. What is sigma n? Sigma n is equal to sigma cos square theta. So see this, sigma n is equal to sigma x cos square theta. So if you put sigma y is equal to 0, you get previous problem. Okay, you get previous problem. So if you analyze this, you could have analyzed the previous problem also. So like that, you get sigma n, sigma theta is sigma x minus sigma y by 2 sin 2 theta. So if you apply sigma y is equal to 0, it is sigma x sin 2 theta by 2, previous problem. Okay. The maximum tangential stress will occur when sin 2 theta becomes 1 or theta becomes 45. So the maximum tangential stress in this case is sigma 1 minus sigma 2 by 2 or sigma x minus sigma y by 2. Sigma x minus sigma y by 2. So resultant stress on the inclined plane is under root of sigma n square plus sigma t square. and where it acts, tan phi is equal to sigma t by sigma n. So same. Now let us take a more general case. If you take a more general case, now we have sigma x is acting in x direction, sigma y is acting in y direction. In addition, we have shear stress tau acting on all the four faces. This is tau here, tau here, this is tau here. So this is the most common case, most general case. Okay, we have sigma x is acting, we have sigma y is acting, we also stress is also acting. So for this, if you consider any inclined plane, at a theta to the vertical plane on which the stress sigma x is acting, there are again we have one normal stress and one tangential stress, Pn and Pt, okay, or sigma n and sigma t. So the normal stress sigma n is equal to sigma x cos square theta plus sigma y sin square theta plus tau sin 2 theta plus tau sin 2 theta. If you put tau is equal to 0, we get the previous problem, sigma x cos square theta plus sigma y sin square theta. Similarly, tangential stress sigma t is equal to sigma x minus sigma y by 2 sin 2 theta minus tau cos 2 theta. For principal planes, tan 2 theta is equal to 2 tau by sigma x minus sigma y. Principal plane is a plane in which there is no tangential stress. So sigma t is equal to 0. For principal plane, sigma t is equal to 0. So equate sigma t is equal to 0. You get from this tan 2 theta is equal to 2 tau by sigma x minus sigma y. So from this formula, we will find out the location of the principal plane. Tan 2 theta is equal to 2 tau by sigma x minus sigma y. We will get theta is equal to half of tan inverse 2 tau by sigma x minus sigma y. That will give you the principal plane. If you add 90 degrees to theta, theta plus 90 gives the second principal plane. We will get the second principal plane. So to find out the principal plane, we have to equate tangential stress sigma t is equal to 0. So from which we get tan 2 theta is equal to 2 tau by sigma x minus sigma y is the location of the principal plane. There are two principal planes satisfying this condition. One is the major principal plane and the other minor principal plane. So if you know theta, the major principal plane, theta plus 90 will give you the minor principal plane. Okay, if you add theta plus 45, you get the plane on which maximum shear stress will take place. Theta plus 45 gives you the plane on which the maximum shear stress is occurring. So for maximum shear stress, you can differentiate d sigma t by d theta is equal to 0, or for you can get from this the maximum shear stress is a sigma x sigma 1 minus sigma 2 by 2. Previous problem I explained. The maximum shear stress is sigma 1 minus sigma 2 by 2, or it is equal to under root of sigma x minus sigma y whole square plus 4 tau square by 2. It is sigma 1 minus sigma 2 by 2. Principal stresses. Sigma 1 and sigma 2 are the principal stresses. So maximum shear stress is sigma 1 minus sigma 2 by 2. So which is nothing but under root of sigma x minus sigma y whole square plus 4 tau square. We can calculate the principal stresses sigma 1 and 2 from this formula. Okay, sigma 1 and 2, sigma is by simply substituting theta is equal to, okay, theta tan 2 theta is equal to 2 tau by sigma x minus sigma y. If you substitute in this equation, sigma n equation, you get the principal stresses. So the principal stresses are sigma x plus sigma y by 2 plus or minus half of under root of sigma x minus sigma y whole square plus 4 tau square. So if a body is subjected to sigma x in the x direction, sigma y in the y direction, and shear stress tau at all the faces, then the principal stresses sigma 1 and sigma 2 are sigma x plus sigma y by 2 plus or minus half of under root of sigma x minus sigma y whole square plus 4 tau square. If you take plus sign, you will get major principal stress sigma 1. If you take minus sign, you get the minor principal stress sigma 2. The maximum shear stress is sigma 1 minus sigma 2 by 2. Sigma 1 minus sigma 2 by 2, 2 by 2, or otherwise sigma x minus sigma y whole square plus 4 tau square by 2. It comes from this sigma 1 minus sigma 2 by 2. So what is the location of the principal plane? The location of the principal plane can be obtained from tan 2 theta is equal to 2 tau by sigma x minus sigma y. Okay, 2 tau by sigma x minus sigma y. That gives theta, the location of the principal plane. Theta plus 90 gives the location of the minor principal plane. The theta plus 45 gives the location of the maximum shear plane. Maximum shear plane. And the maximum shear stress is sigma 1 minus sigma 2 by 2. So this is the concept. This is very important. If you just understand this one slide, it is good enough. Because from this you can get everything. If you put sigma x, sigma y is equal to 0 and tau is equal to 0, we get the first problem. If you substitute tau is equal to 0, we get the second problem. So if you remember this, we get the most general problem. This is the most general case. So you try to keep this PPT. You try to understand this PPT nicely. So here we are calculating the principal stresses, their location and the maximum shear stress and its location. So same problem, if there is only pure shear stress, sigma x is equal to 0, sigma y is equal to 0. Put sigma x is equal to 0 and sigma y is equal to 0 from the previous problem. There is only tau. So sigma n is equal to tau sin theta, sigma tangential is equal to tau cos theta. Okay. The resultant stress is sigma n square plus sigma t square. So simple. The principal planes, the principal stresses can also be computed with the help of a Mohr circle. Okay. The principal planes and the principal stresses can be found out with the help of a Mohr circle. So let us consider a case, the most general case. Sigma x is acting in the x direction, sigma y is acting in the y direction, tau is acting on the R4 faces. So just a previous problem, previous slide, this slide. So for this I will explain you how to draw the Mohr circle. So if you know this, you can draw the Mohr circle for any case, because if you put sigma y is equal to 0, tau is equal to 0, you get purely axial sigma x condition. If you put only tau is equal to 0, we get sigma x, sigma y condition. So if you understand the Mohr circle for the most general case, you can draw the Mohr circle for any problem. Okay. So Mohr circle is a graphical representation to find out the principal planes and the principal stresses. Mohr circle is a graphical representation to obtain the principal planes and principal stresses. So how to draw the Mohr circle? Let us consider an x-axis and also a y-axis. O is the origin where x-axis and y-axis are meeting. Okay. We have sigma x and sigma y are acting in the plane. So these are normal stresses. Normal stresses are denoted on x-axis and shear stresses are denoted as the y-axis. Okay. Shear stresses are denoted as the y-axis. Okay, you understand? So now let us draw certain, you choose certain scale. Okay, say for example 10 Newton per mm square is equal to 1 centimeter. So to draw to certain scale, sigma x is nothing such that OA on the x-axis. You draw OA. OA is equal to sigma x. Say for example, sigma x is equal to 50 Newton per mm square. So as per 10 Newtons per mm square is equal to 1 centimeter, OA will be equal to 5 centimeters. So put 5 centimeters, you get the point A. Okay, because sigma x is tensile, I am drawing it to the positive side. Now in the case sigma y is also tensile, so I am drawing sigma y also on the positive side. So draw sigma y OB such that it is equal to sigma y. Say sigma y is equal to 20, let us say. This is 50, this is 20. So OB will be 2 centimeters. So take a scale and draw OA and OB. So now you got point A and as well as the point B. We got point A as well as the point B. You know the radius of the circle. Now what you have to do is, After drawing point A and point B, bisect AB. Bisect AB such that you get the center point C. Such that you get the center point C. Bisect AB such that you get the center point C. Okay? Center point C. Now, what you have to do? With OA, you draw a circle. We draw a circle with OA or OB as radius. Draw a circle. This will again cut the x-axis at A and B. It cuts the x-axis at A and B. Okay. So just follow. Draw to the scale. Please draw to the scale such that sigma x is equal to OD. Sorry, I said you wrong. So just correct it. Draw to the scale sigma x is equal to OD. OD is equal to 5 centimeters if you take 50. Similarly, sigma y is equal to OE. OE. So you don't get A, B points. Okay. First you got point D and point E. So OA is equal to sigma x. OE is equal to sigma y. Okay. So for some scale you draw OD and you draw OE. So you get point D and E. Now at point D you draw a perpendicular line such that it is equal to tau. Say tau is equal to 30 Newton per mm square. So this vertical line is 3 centimeters. Okay, to the scale it will be 3. So draw a 3 centimeters line perpendicular to D such that you get the point F now. Such that you get the point F now. Similarly, at E, downward, because shear stress is complementary. If it acts on one plane upward, it automatically acts downward on the other plane. So you draw the shear stress downward at the point E. So you draw a vertical line equal to tau to the same scale. So you get F and G. Okay, you get F and Z. Okay. Now you locate the center of ED. You have ED. So locate the center of ED as C. Okay. You locate the center of the ED as C. Now with C as center, CF or CG as radius. With C as center, CF or CG as radius, draw a circle which cuts the x-axis at A and B. Which cuts the x-axis at A and B. Now if you measure OA, you get the major principal stress. If you measure OB, you get the minor principal stress. And if you measure the angle CAF, okay, FCA, angle ACF or FCA, that gives angle 2 theta of the major principal plane. So take half of that, you get theta, that is the location of the major principal plane. Add 90 to this, you get the minor principal plane. So from Mohr circle also, you can obtain the shear principal planes and principal stresses. So observe this, any point on the Mohr circle, the x coordinate represents the normal stress, the y coordinate represents the shear stress. X coordinate represents the normal stress and the y coordinate represents the shear stress. So any point on the Mohr circle, the coordinates of any point on the Mohr circle represents a normal stress and a shear stress. A normal stress and a shear stress. So you have to understand this. Any point on the Mohr circle will have coordinates. X coordinate is the normal stress and y coordinate is the shear stress. So before proceeding, I will once again explain the procedure for drawing the Mohr circle. So just see our problem. This block is subjected to a horizontal stress sigma x, a vertical stress sigma y, and the shear stress on all the 4 planes. I want to draw the Mohr circle for this case and find out what is principal stresses sigma x, sigma 1 and sigma 2, and also its location. That's what I want to do. So draw x-axis and y-axis. Draw x-axis and y-axis. On x-axis, you draw such that you choose a scale. Some 10 newtons per mm square is equal to 1 centimeter. So to a certain scale, you draw OD such that OD is equal to sigma x. So if sigma x is equal to 50 Newton per mm square, OD will be equal to 5 for the scale. So put 5 centimeters from O, you get point D. Now similarly, sigma y is equal to 20, let us say. So OE is equal to 2 centimeters. So you are getting point D and point E on the x-axis. So now we know point D and point E on the x-axis. At D, draw a perpendicular line to the x-axis equal to a length of tau. Say tau is equal to 30 newtons per mm square. So you have to draw 3 centimeters perpendicular. Draw a line perpendicular to x-axis at D for a length of 3 centimeters. Similarly at E, draw downward tau, another 3 centimeters, draw another downward. So now you got point F and point G. Okay, now you got point F and point G. Now what you do? You know point D and point E. You just divide point DE to its center. So that center is C. So find out the center of DE. You get C. Now with C as center, with CF or CG as radius, draw a circle which is called as a Mohr circle. This circle will cut the x-axis at 2 points, A and B. So from this, if you measure OA, you are going to get the major principal stress to the scale. Say for example, OA is equal to 6 centimeters. So then the major principal stress is 6 into 10, 60 newtons per mm square. Okay, so you get OA and the minor principal stress OB. So if you measure OB, say 1 centimeter, so it will be minor principal stress is 1 into 10, 10 Newton per mm square. So like that, by measuring OA and OB, you can get the major principal stress and minor principal stress. And if you measure angle FCA or ACF, if you measure this angle, that will give you 2 theta. So 2 theta, if you just divide by 2, you get the theta, which is the location of the major principal plane. If you add 90 degrees to theta, you get the minor principal plane. So like this, you can get the major and minor principal stresses from the diagram. On any point on the Mohr circle will have 2 coordinates, x coordinate as well as y coordinates. X coordinate will be normal stress and y coordinate will be tangential stress or the shear stress. So if you take point A, if you look at the point A on the Mohr circle, it is on the x-axis. Point A is on the x-axis. So at point A, there is only normal stress, there is no tangential stress. So that is why point A represents the principal plane. Similarly, if you see point B, it is also on the x-axis. So there is no tangential stress. So B, it is 0. Tangential stress, because it is on the x-axis, there is no y coordinate. There is no shear coordinate. So that is why for point A and B, they represent the principal stresses. OA is equal to sigma 1, the major principal stress. OB is equal to sigma 2, the minor principal stress. Also find out the square. Tan 2 theta, the location of the principal plane is epsilon xy by epsilon y minus epsilon 2. So you can find out the principal strains also. If you know the principal strains, if you know the principal stresses, say sigma 1 and sigma 2 are the principal stresses. Sigma 1, sigma 2, sigma 3, if it's a 3-dimensional case, the principal strains can be obtained from sigma 1, sigma 2, sigma 3 also. From generalized Hooke's law. Epsilon 1 is equal to sigma 1 minus E minus 1 by m times sigma 2 by E minus 1 by m times sigma 3 by E, where 1 by m is Poisson's ratio. Okay, direct strain is divided by E and lateral strain will be, similarly epsilon 2 will be sigma 2 by E minus 1 by m times sigma 1 by E minus 1 by m times sigma 3 by E. Similarly epsilon 3 will be equal to epsilon 3 by E, the shear strain phi max will be equal to epsilon 1 minus epsilon 2 for a two-dimensional stress system. So for strain energy is so the work done by the forces is stored as strain energy within the body of sigma 1 epsilon 1 plus half of sigma 2 epsilon 2 plus half of sigma 3 epsilon 3, where epsilon 1 epsilon 2 epsilon 3 are the principal strains. Okay, these are equal to principal strains. So sigma 2 sigma 2 sigma 3 sigma 3 sigma 1. For a two-dimensional system, there will only sigma 1 sigma 2 will be there, sigma 3 is equal to 0. So if you substitute, the strain energy is equal to 1 by 2e into sigma 1 square plus sigma 2 square minus 2 by me. Sigma 1 minus 2 is equal to epsilon 3 is equal to, here I given three equations. So solving these three simultaneous equations, if you know epsilon 1, epsilon 2, epsilon 3 and the Young's modulus and the Poisson's ratio 1 by m, you can solve these three equations to obtain sigma 1, sigma 2 and sigma 3. So if you solve that, you get sigma 1, sigma 2, sigma 3 as these equations. I don't recommend that you remember these equations. You write, easily remember this. Sigma 1 is equal to e by 1 minus mu square into epsilon 1 plus mu times epsilon 2. Sigma 2 is equal to e by 1 plus mu square into mu times epsilon 1 plus epsilon 2. So like that you can obtain sigma 1 and sigma 2 once you know the epsilon 1 and epsilon 2 in case of a two-dimensional situation. So the maximum shear strain xy associated with axis 45 degrees to the direction of the principal plane, just like what we have done for stresses. Phi max by 2 is equal to epsilon x minus epsilon y by 2 whole square plus phi xy by 2 whole square. So let us try to solve some problems now. So here what we have to remember, the concept is if we have a three-dimensional body subjected to the forces, if subjected to forces, any inclined plane will have stresses normal to it and the tangential to it. The stress normal to the inclined plane is sigma n. The stress tangential to the inclined plane is sigma t. If the plane is such that sigma t is equal to 0, the tangential stress is equal to 0, the plane is called as a principal plane. A plane on which there is only normal stress and there is no shear stress, such a plane is called as the principal plane. So for a three-dimensional situation, we have three principal planes. Okay. The stress acting on the principal plane is called as the principal stress. The highest of is called major principal stress. The least of this is called as minor principal stress. The other one is called as the intermediate principal stress. But if we take a two-dimensional situation, we have only two principal planes and two principal stresses. Okay. So these principal planes and principal stresses can also be obtained by drawing the Mohr circle. Okay, by drawing the Mohr circle. So this is the concept. Just like principal planes, we can draw our principal strains also. That's what we have to consider. So with this simple concept, try to solve these problems. If an element of a stressed body is in a state of pure shear with a magnitude of 80 Newton per mm square, the magnitude of maximum principal stress at that location is. Here he has given sigma x is equal to y, sigma x is equal to 0, sigma y is equal to 0, and he wants us to find out the major principal stress. Tau is 80 newtons per mm square. You know sigma 1, the major principal stress sigma 1 is equal to sigma x plus sigma y by 2 plus half of root of sigma x minus sigma y whole square plus 4 tau square. So if you solve this, sigma x is equal to 0, sigma y is equal to 0. If you substitute, you get sigma 1 is equal to tau. Tau is nothing but 80 Newton per mm square. So the maximum principal stress is 80 Newton per mm square tensile. Because it's positive, it is tensile stress. Pick the incorrect statement from the following four statements. On the plane which carries maximum normal stress, the shear stress is 0. On the plane which carries maximum normal stress, the shear stress is 0. Principal planes are mutually orthogonal. On the plane which carries maximum shear stress, the normal stress is 0. The principal stress axes and principal strain axes coincide for an isotropic material. So we have to select the incorrect statement. So first of all, let us see the first statement. On the plane which carries maximum normal stress, the shear stress is 0. The maximum normal stress is the major principal stress. So there's a major principal plane. So the plane carrying the major principal stress is major principal plane. So principal plane means there is no shear stress. So A is correct. A statement is correct. Now let's go to see B. Principal planes are mutually orthogonal. Yes, correct. All the three principal planes are mutually orthogonal. So X, Y and Z. They are three mutually orthogonal. So statement B is correct. On the plane which carries maximum shear stress, the normal stress is 0. It is not correct. Okay, the plane which carries maximum shear stress will also contain certain amount of normal stress. So C is incorrect. What is D? The principal axis and principal axis coincide for answer. Yeah, correct. Principal stress axis and principal strain axis are same. They are not different for an isotropic material. An isotropic material is a material which has got same properties in all the directions. Such a material is called as isotropic material. So for an isotropic material, the principal stress axis or strain axis is same. There is no difference. So C is the incorrect statement. The state of two-dimensional stress acting on a concrete lamina consists of a direct tensile stress sigma x is equal to 1.5 newtons per mm square and shear stress is equal to 1.2 newton per mm square. What is the tensile strength of the concrete in newton per mm square? It is asking. So in other words, what is he asking? He is asking major principal stress he is asking. So here it is a case of sigma x, sigma y is equal to 0. Tau is existing, but sigma y is equal to 0. Sigma x is equal to 1.5, sigma y is equal to 0, tau is equal to 1.2. So we substitute sigma 1, 2 is sigma x plus sigma y by 2 plus or minus half of root of sigma x minus sigma y whole square plus 4 tau square. So if you substitute this, sigma y is equal to 0 and sigma x is equal to 1.5, tau is equal to 1.2, you get major principal stress as 2.17 Newton per mm square because that is causing the cracking of the concrete. Major principal stress 2.17. C is the correct answer. In a two-dimensional stress analysis, the state of stress at a point is shown below. If sigma is equal to 120 megapascals and tau is equal to 70 megapascals, then what is sigma x and sigma y? He is asking us to find out. Okay, he is given an inclined plane. Okay, he is giving normal stress sigma 120 megapascals and the tangential stress 70 megapascals. So he is asking us to find out what is sigma x and sigma y. So it is very simple. Okay, there is no tau here. So sigma x is there, sigma y is equal to here, tau is not there. So let us take this problem. Sigma is equal to 120 megapascals and tau is equal to 70 megapascals. So considering the horizontal equation, instead of this, you don't bother about this. What you can do is, you go back to this equation. You go back to this equation. You have sigma normal is equal to sigma x cos square theta plus sigma y sin square theta plus tau sin 2 theta. Tau he has given 0. So we have sigma normal is equal to sigma x cos square theta, sigma y sin square theta. Okay, he has given what is the sigma n. He has given us what is sigma n. Sigma t is equal to sigma x minus sigma y by 2 sin 2 theta. Tau is not there. So substitute sigma x and sigma y values. Sigma n and sigma t values are given. We want to find out sigma x and sigma y. So two equations and two unknowns solve from sigma x and sigma y from this equation. This is good enough. We need not really worry about anything else. So taking from this concept, sigma n is equal to sigma x cos square theta plus sigma y sin square theta. Sigma t is equal to sigma x minus sigma y by 2 sin 2 theta. So he has given you what is sigma n and what is sigma t. So you just substitute these values, you get solve these two equations, you are going to get the solution for this. So nothing to bother much about that. So from this you can solve sigma x and sigma y. Symmetry of stress tensor at a point in the body under equilibrium is obtained from is actually out of syllabus for you, but it is the symmetry of the stress tensor is obtained from moment equilibrium equations. This is moment equilibrium equations. It is out of syllabus, I think. If principal stresses in a two-dimensional case are 10 minus 10 megapascals and 20 megapascals respectively, then maximum shear stress at the point is giving two principal stresses. Sigma 1 is equal to minus 10. Sorry, sigma 1 is equal to 20. Major principal stress is 20 and minor principal stress is minus 10. So sigma 1 is equal to 20. Minor principal stress is sigma 2 is minus 10 and asking us to find out the maximum shear stress. Sigma 1 minus sigma 2 by 2 is the maximum shear stress. So the maximum shear stress is sigma 1 minus sigma 2 by 2. 20 minus of minus 10 by 2. So 30 by 2, 15 megapascals is the maximum shear stress. Where does this maximum shear stress will act? This acts on a plane at a degrees of 45 degrees to the major principal plane. Okay, it acts at 45 degrees to the major principal plane. The necessary and sufficient condition for a surface to be called as a free surface is no stress should be acting on it, tensile stress acting on it must be 0, shear stress acting on it must be 0, no point on it should be under any stress. Free surface is the surface on which there is no shear stress. Free surface is a surface subjected to constant normal stress and 0 tangential stress. So such a surface is called as a free surface. So C is the answer. C is the answer. Mohr circle for the state of stress is defined by 30 0 0 30 MPa. So this is the state of stress. 30 0 0 30 is a circle with where is the center and what is the radius is asking. Okay, first try to understand this. What is the stress defined by 30 0 0 30? This is the normal stresses. Okay, this is the normal stress. Sigma 1 is equal to 30 megapascals and sigma 2 is equal to 30 megapascals. The shear stress is 0 because it's a principal stress. The shear stress is 0. So sigma 1 is equal to 30, sigma 2 is equal to 30, and so what is happening? Sigma 1 is equal to 30, sigma 2 is equal to 30. What is the radius of the Mohr circle? Radius of the Mohr circle is equal to sigma 1 minus sigma 2 by 2. Diameter of the Mohr circle is sigma 1 minus sigma 2, or radius of the Mohr circle is sigma 1 minus sigma 2 by 2. So radius of the Mohr circle is equal to 0. Radius of the Mohr circle is sigma 1 minus sigma 2 by 2 is equal to 0. So where does the center lies now? Center lies sigma 1 is equal to 30 megapascals, sigma 2 30 megapascals. So both are at the same point. Radius is equal to 0. So the same point is the center. It is a center. It is one point, single point of radius 0 with at 30 and 0 as the coordinates. So from this center at 0 0 and radius 30 megapascals. No, correct, not correct. Center at 0 0 and radius the 60 wrong. Center at 30 0 and radius 30 wrong. Center at 30 0 and 0 radius. This is the correct answer. D is the correct answer. An axially loaded bar is subjected to a normal stress of 173 megapascals. The shear stress in the bar is very simple. And there is no other stress. It's the uniaxial stress. Okay, there is a uniaxial stress. Shear stress is sigma 1 minus sigma 2 by 2. So here sigma 2 is not there. So it is sigma 1 by 2. It is sigma 1 by 2. So 173 by 2, 86.5 megapascals is the answer. Where does this plane acts? The shear plane at 45 degrees to the vertical plane. So this is the plane on which the major principal stress, only one principal stress is acting. So it will act at 45 degrees for this plane on which the shear stress is maximum. The shear stress is maximum. Consider the following statements. On a principal plane, only normal stress acts. On a principal plane, only normal stress acts is correct. On a principal plane, both normal and shear stresses act. No, it is wrong. On a principal plane, only normal stress acts. On a principal plane, only shear stress acts. Wrong. Principal stress on principal plane, shear stress is 0. So there is no shear stress. Isotropic state of stress is independent of frame of reference. Because in isotropic state of stress, the properties are same in any direction. So there is no need of any reference direction. So isotropic state of stress is independent of frame of reference. So statement 4 is correct. So which the true statements, which are the two statements? Principal plane only normal stress acts. This is correct. 1 is correct and 4 is correct. So 1 and 4 are correct. So the correct answer is A. The major and minor principal stresses at a point are 3 megapascals and minus 3 megapascals. The maximum shear stress of the point is sigma 1 is given, sigma 2 is given. The maximum shear stress is sigma 1 minus sigma 2 by 2. So 3 minus of minus 3 by 2, that is equal to 6 by 2 is a 3 megapascals. That is the maximum shear stress. Where does this maximum shear stress act? It acts on a plane at 45 degrees to the plane on which 3 megapascals is acting. Okay, major principal plane. It acts at 45 degrees to the major principal plane. If a small concrete cube is submerged deep in still water in such a way that the pressure exerted on all faces of the cube is P, then the maximum shear stress developed inside the cube is. So here it is a hydrostatic pressure. It is a hydrostatic pressure. So on all faces there will be equal amount of the water pressure. The water pressure is equal to W into H. If the block is immersed at a depth of H, if W is the density of the water, so WH is the pressure. So this pressure is giving us P. Okay, this pressure is giving us P. So sigma x is equal to sigma y is equal to sigma z is equal to P. He is giving. Since only one normal force is acting, there is no shear stress. You can see there is no shear stress on any plane in the water. So tau is equal to 0. So what is tau max? Sigma 1 minus sigma 2 by 2 or sigma 2 minus sigma 3 by 2. Whatever you take, it is P minus P by 2. So it is equal to 0. P minus P by 2 is equal to 0. So answer is 0. 0 is A is the correct answer. The state of two-dimensional stress at a point is given by the following matrix of stress. Sigma xx, sigma xy, sigma xy, sigma yy. So this is 100, 30, 30, 20. So sigma x is equal to 100. Okay, sigma y is equal to 20. Okay, and sigma xy, that is tau xy, the shear stress is 30. Okay, the shear stress is 30. Sigma xy is nothing but the shear stress acting on the xy plane. So sigma x is equal to 100, sigma y is equal to 20, tau xy is equal to 30. So you want us what is the maximum shear stress. First find out, you can find out tau max directly, or you can find out you can sigma 1 and sigma 2 and then take sigma 1 minus sigma 2 by 2. But we know tau max is equal to sigma 1 minus sigma 2 by 2. So which is equal to sigma x minus sigma y whole square plus 4 tau square by 2. So sigma x minus sigma y whole square plus 4 tau square by 2. Sigma x is equal to 100. Sigma y is equal to 20. Tau xy is equal to, tau is equal to 30. So if you substitute here, you directly get the maximum shear stress as 50 newtons per mm square. For the state of stress in megapascal shown in figure below, what is the maximum shear stress in megapascals MPa? So see here, he is giving sigma x is equal to 2 megapascals compressive, sigma y is equal to 4 megapascals tensile, and shear stress is equal to 4. Tau is equal to 4. So sigma x is equal to 2 megapascals minus sigma y is equal to 4 megapascals plus tau is equal to 4 megapascals. So the maximum shear stress is sigma 1 minus sigma 2 by 2 plus half of sigma x minus sigma y whole square plus 4 tau square. So this is half of sigma x minus sigma y whole square plus 4 tau square gives us the maximum shear stress. Only thing is sigma x you have to substitute as minus 2. Sigma y is equal to 4 you have to substitute. Tau is equal to 4. You get the answer as 5 megapascals. Two triangular wedges are glued together as shown in the following figure. The stress acting normal to the interface sigma n is so simple. He has given sigma x, he has given sigma y, and he wants us to find out sigma n. Okay, he wants us to find out sigma n. So this is sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta. Or otherwise sigma n is equal to sigma x cos square theta plus sigma y sin square theta. Any one formula you can use. So here sigma x is equal to 100, sigma y is equal to minus 100, you have to substitute. So if you substitute, you are getting 0. Answer is 0. Okay, simple. Just use the concept, that's all. For the plane stress situation shown in the figure, the maximum shear stress on the plane on which it acts are. He has given sigma x as 50 megapascals, sigma y is equal to 50 megapascals, tau is equal to 0. Okay, tau is equal to 0. So what does he want? The maximum shear stress. Maximum shear stress is sigma 1 minus sigma 2 by 2. So this is, see here there is no shear stress. So this plane itself is the principal plane. This plane itself is another principal plane. Okay, so sigma 1 is equal to 50, sigma 2 is equal to 50. The maximum shear stress is sigma 1 minus sigma 2 by 2. So 50 minus 50 by 2 is equal to 0. So this 0 is the answer. 0 in any direction, it is 0. For the stress state in megapascal shown in figure, the major principal stress is 10 megapascals. He has given us sigma 1. What is the shear stress he is asking? He has given us the major principal stress sigma 1 and he is asking what is tau. So he has given us sigma x, he has given us sigma y, but tau is also there, but we don't know the tau value. He wants us to find out this tau value. Okay, he wants us to find out this tau value. So major principal stress is 10 megapascals, that's what he has given. So sigma x is equal to 5, sigma y is equal to 5. Substituted in sigma 1. Sigma 1 is equal to sigma x plus sigma y by 2 plus half of under root of sigma x minus sigma y whole square plus 4 tau square. Tau is the unknown. Tau is the unknown. Sigma 1 is given as 10. So only there is one unknown in this equation. So you solve for tau value. Tau you get 5 megapascals. So simple, just concept. Use sigma 1 is equal to sigma x plus sigma y by 2 plus half of under root of sigma x minus sigma y whole square plus 4 tau square. A plate in equilibrium is subjected to uniform stresses along its edges with sigma x is equal to 30, sigma y is equal to 50 as shown in the figure. The Young's modulus of the material is 2 into 10 to the power of 11 and the Poisson's ratio is 0.3. If sigma zh is negligibly small and assumed to be 0, then what is the strain sigma z or epsilon z? He wants us to find out epsilon z. So see here what he has given. He has given us sigma x. Okay, he has given us sigma x 30 megapascals. He has also given us sigma y is equal to 50 megapascals. Both are tensile. And he is saying that sigma z is 0. He is also saying that sigma z is equal to 0. And I want us to find out epsilon z. So epsilon z, what is the strain in z direction? Strain in z direction is equal to epsilon z by E. Okay. Strain in z direction is equal to epsilon z by E minus 1 by m times or mu times sigma x by E minus mu times sigma y by E. But epsilon z, sigma z has given as 0. So sigma z by E, see strain in z direction is equal to, strain in z direction is equal to sigma z by E minus mu times sigma x by E minus mu times sigma y by E, where mu is equal to 1 by m is equal to Poisson's ratio. Sigma x is 30, sigma y is equal to 50, E is 2 into 10 to the power of 11, mu is equal to 0.3. So substitute in this equation, sigma z is equal to 0. you get epsilon z is equal to minus mu times sigma x by E minus mu into sigma y by E, or if you take minus mu common, minus mu into sigma x plus sigma y by E. Sigma z is 0, don't bother. So if you substitute, you will get epsilon z. For a plane stress problem, the state of stress at a point P is represented by the element shown in figure. What he has given? Sigma x is equal to 80 megapascals tensile. Sigma y is 20 megapascals compressive, so minus 20, and tau is equal to 25 megapascals. So what he want? By how much angle theta in degrees, the stress element should be rotated in order to get the planes of maximum shear stress. So he is asking us the plane of maximum shear stress. Okay, the plane of maximum shear stress. So he has given sigma x is 80, sigma y is equal to minus 20, compression tau is equal to 80A. So we know the location of the principal stress tan 2 theta is equal to 2 tau by sigma x minus sigma y. 2 into shear stress is minus 25, 80 minus compression. So it doesn't matter whether you take minus sign or plus sign for the shear. There it comes here also. So if you take this, theta is equal to, you get tan 2 theta value. So if you get tan 2 theta value, you get 2 theta value. So the angle plane of maximum is theta plus 45. Alpha is equal to theta plus 45. Or if you want to follow the sign convention for shear stress, I'll just explain this with the previous figure. See here, this type of shear stress is called a negative shear stress. So this is providing a clockwise moment. A clockwise moment, a shear causing a clockwise moment is negative, and a shear causing an anti-clockwise moment is negative. So if the shear is upward like this, then it is a positive shear stress. Here it is a negative shear stress. That's why we have put minus 25 here. Tau is, oh sorry, yeah, is a minus sign we have used. Tau is, what is the value of tau he has given? Yeah, the tau value is 80 megapascals. 25. Tau value is 25 megapascals. It is wrong here. Tau is equal to 25 megapascals, not 80 megapascals. It is 25 megapascals. Tau is equal to 25 megapascals, but it is taken negative because on this plane the shear is acting downwards. It is negative. If it is acting upwards, we take it as a positive shear stress. What you have to remember is, if it provides a clockwise movement, then it is a negative shear stress. If it is a anti-clockwise shear, it creates an anti-clockwise movement, then the shear is positive. Do not worry about more circle methods. So that is what I wanted to explain to you in principal stresses and principal strains. Actually, principal stresses and principal strains is not in the syllabus for your 2020. If I look at the 2020 syllabus downloaded from IIT Delhi website, the GATE examination 2020 was conducted by IIT Delhi. So from their website I have downloaded, and if you see this principal stresses and strains is not there in your syllabus. It was there previously, but it is not there in 2020. I don't know in 2021 whether they are going to include it or not. But I thought, if you want to understand the theories of failures, which is there in the syllabus 2020, you need to understand the principal stresses. So that is why I thought I will spend some time on explaining you the principal stresses and strains. So please understand that if there is any plane, you are considering, there will be a normal stress and tangential stress. So the normal stress is equal to sigma x cos square theta plus sigma y sin square theta minus tau sin 2 theta. So sigma, and similarly sigma y. Because of sigma x and sigma y and tau, we have normal stress and the tangential stresses. The plane on which the tangential stress is equal to 0, we call it as the principal plane. So we have, for a three-dimensional situation, three principal planes. The normal stress acting on the principal plane is called as principal stress. So we have three principal stresses. The maximum is called major principal stress. The minimum is called the minor principal stress, and the other one is called as the intermediate principal stress. So if you take a two-dimensional stress situation, the principal, we have only two principal planes and two principal stresses, sigma 1 and sigma 2. The maximum shear stress is sigma 1 minus sigma 2 by 2. Okay, sigma 1 minus sigma 2 by 2. The location of the principal plane, you can find out principal planes and principal stresses from sigma 1 2 is equal to sigma 1 2 is equal to sigma x plus sigma y by 2 plus or minus under root of sigma x minus sigma y by 2 whole square plus tau square shear stress. So like that you can find out the principal stresses. The maximum, the location of the principal plane can be find out tan 2 theta is equal to 2 tau by sigma x minus sigma y. You can find out the 2 theta, if you divide by 2 you get theta, that is the location of the major principal plane. So if you add 90 degrees, theta plus 90, you get the minor principal plane. The maximum shear stress is equal to half the difference of the principal stresses, that is half of sigma 1 minus sigma 2. The plane on which the shear stress, the maximum shear stress acts is at 45 degrees to the major principal plane. So if the location of the major principal is theta, theta plus 45 is the plane on which the maximum shear stress acts. So these are the basic concepts you need to remember in this particular chapter, and with these concepts you will be able to easily understand and solve any problem coming from principal stresses and strains, and also the Mohr circle. I have also explained how to draw the Mohr circle diagram. From this you can easily understand the theories of failure chapter, which we are going to discuss tomorrow. So please come prepare with the concepts of principal stresses and strains tomorrow. We are going to discuss theories of failure tomorrow. These concepts are very much useful for tomorrow's chapter. So thank you very much for your kind listening. I hope you enjoyed today's session. It's a very important session for structural engineers in whether gate point of view or otherwise also. Calculation of principal stresses is very important for structural engineers. So I hope you enjoyed this particular session. Thank you very much for joining. Hope you join more in number and try to learn more from us. We are trying to spend a lot of time in delivering these lectures for you, taking a lot of strain. So I hope more and more number of students you join and listen to our live lectures. The link, you can obtain the link for the YouTube from your friends also. And if you are not registered, you can obtain the link from your friends in the WhatsApp or in the mail, and you can join the video lecture by clicking the mail. It is not necessary that you should have registered for this. So you can just take the link from your friends and join the live video sessions. So I expect more and more number of students join for theories of failure, which explains how a structure is going to fail, under what conditions the structure is going to fail. So the theories of failure will tell you how we will identify the failure in a structure. So it's a very important topic for structural engineers. So I hope more and more number of students will join to listen theories of failure chapter tomorrow. Thank you very much. Have a nice evening. Tata, bye bye. Take care of yourself and take care of your elders. Have a good evening. Bye. Thank you. Take care.